The cosmic horizon. Since the dawn of consciousness, humanity has looked to the heavens in wonder. The glittering points of light in the velvet darkness have been our guides, our gods, and our greatest mystery. The questions our distant ancestors asked around crackling fires are the same questions we ask today with our most powerful instruments. Where did all of this come from? What is our place within it? And how far does it all go? To answer these questions, we have embarked on the greatest journey of exploration imaginable. Not a journey in a physical vessel, for the distances are too vast. Instead, it is a journey through time. When we look out into the cosmos, we are not seeing things as they are, but as they were. We are looking at ghosts of light, echoes from a past so deep it challenges the limits of our comprehension. This is the story of that journey to the farthest reachable point, not in space, but in time. This is a voyage to the edge of the visible universe, to a place we call the cosmic horizon. Reflections in time, the most fundamental concept in our journey, is both simple and profound. Light does not travel instantaneously. It moves at a finite, albeit incredible, speed, approximately 300,000 kilometers per second. This cosmic speed limit means that every ray of light carries with it a story from the past. When we look at the moon, we see it as it was 1.3 seconds ago. The mighty sun, the heart of our solar system, appears to us as it was 8 minutes and 20 seconds in the past. If the sun were to vanish at this very moment, we would continue to feel its warmth and see its light for over 8 minutes, blissfully unaware of our doom. This time delay effect becomes staggering as we look beyond our immediate solar neighborhood. The nearest star to our sun, Proxima Centauri, is 4.2 light-years away. The light we see from it tonight began its journey toward Earth over 4 years ago, when the world was a different place. The beautiful Andromeda Galaxy, a sister spiral to our own Milky Way, and the most distant object visible to the naked eye, is 2.5 million light-years away. When the light we see from Andromeda tonight left its source, early human ancestors were just beginning to walk the plains of Africa. This principle transforms astronomy into a form of archaeology. The farther we look into space, the deeper we look into time. The universe becomes a grand cosmic book, its pages measured in light years. For decades, we have been building ever more powerful eyes to read this book, to turn back its pages to the very beginning. Telescopes on Earth and in space, like the legendary Hubble, have taken us billions of years into the past, revealing a universe filled with mature, well-formed galaxies, much like our own. But humanity's curiosity is insatiable. We wanted to see further, to a time before these grand galaxies existed. We wanted to witness the universe in its infancy, the era of the very first stars and galaxies, a period known as the cosmic dawn. To do that, however, we had to overcome a fundamental barrier. The stretching of light. We are all familiar with the Doppler effect. The siren of an ambulance sounds higher in pitch as it approaches and lower as it moves away. This happens because the sound waves are compressed as the source comes closer and stretched as it recedes. The same principle applies to light. In the 1920s, astronomer Edwin Hubble discovered that the universe is not static, it is expanding. With very few exceptions, every galaxy is moving away from every other galaxy. And the farther a galaxy is from us, the faster it is receding. This has a profound effect on the light that travels from those distant galaxies to us. As light journeys across the expanding fabric of spacetime, its waves are stretched. This stretching shifts the light towards the red end of the electromagnetic spectrum in a phenomenon known as redshift. The greater the distance, the greater the redshift. The light from the most distant objects in the cosmos, the very first sources of light in the universe, has traveled for over 13 billion years through an ever-expanding space. Consequently, its light has been stretched so profoundly that it is no longer visible light at all. It has been shifted completely out of the spectrum our eyes can see. past the red, and deep into the infrared portion of the spectrum. To see the universe's first light, to witness the cosmic dawn, we needed a new kind of eye. We needed a telescope capable of peering into the invisible infrared universe with unprecedented sensitivity. It would have to be colossal, incredibly cold, and positioned far from the heat and glare of the Earth. A new eye on the universe that eye was built. Its name is the James Webb Space Telescope. A marvel of modern engineering, JWST is nothing short of a time machine. Its primary function is to capture the faint, ancient infrared light that has been traveling across the cosmos for billions of years. To do this, it employs a magnificent 6.5-meter primary mirror composed of 18 hexagonal segments coated in a whisper-thin layer of gold, which is exceptionally reflective of infrared light. To detect these incredibly faint heat signals from the dawn of time, the telescope itself must be phenomenally cold, just a few tens of degrees above absolute zero. Any warmth from the telescope would blind it, drowning out the ancient signals. To achieve this, it is protected by a 5-layered sun shield the size of a tennis court, which permanently blocks out light and heat from the sun, Earth, and Moon. Launched on Christmas Day in 2021, the James Webb Space Telescope traveled 1.5 million kilometers from Earth to its operational orbit. When it finally opened its golden eye, humanity held its breath. What it revealed was more spectacular than we had ever dared to imagine. Witnessing the cosmic dawn. One of Webb's first images, a deep field view known as SMACS 0723, electrified the world. Pointed at a patch of sky no larger than a grain of sand held at arm's length, it revealed a treasure trove of light. Nearly every speck of light in the image is not a star, but an entire galaxy, each containing billions of its own stars. In the foreground, we see massive, mature galaxies whose light has taken several billion years to reach us. But the image also contains a remarkable trick of nature. The immense mass of the foreground galaxy cluster warps the fabric of spacetime around it, acting as a natural cosmic magnifying glass. This phenomenon, called gravitational lensing, was predicted by Albert Einstein. It bends and magnifies the light from even more distant galaxies hiding behind the cluster, allowing Webb to see objects that would otherwise be far too faint and far too small. Using this natural telescope, astronomers began to find what they were looking for. As they analyzed the light from the most reddened, most stretched out points of light, they were peering back over 13 billion years into the past. Here, in the universe's toddler years, the galaxies look profoundly different. They are not the grand spirals we know, but small, clumpy, irregular knots of brilliance. They are intensely blue, a sign they are ablaze with legions of massive, young, ferociously hot stars. This was the chaotic, violent, and formative era of the cosmos. And then, Webb pushed even deeper. It found candidates for the most distant galaxies ever seen, lighted up. We are seeing the first glimmers of the cosmic dawn. This is the farthest view humanity has ever had of a physical object. Yet our journey is not over. There is a place even further back in time, a final wall that we can look to. The wall of light. To understand this ultimate limit, we must go back even further, before the first stars ever formed. For the first 380,000 years after the Big Bang, the universe was an unimaginable place. It was a searingly hot, incredibly dense, and completely opaque fog. The entire cosmos was a seething soup of fundamental particles, protons, neutrons, and electrons, which were too energetic to bind together to form stable atoms. In this primordial plasma, light could not travel freely. A photon of light would be emitted, only to immediately collide with a free-roaming electron and be scattered in a random direction. Light was effectively trapped, bouncing around like a pinball in an infinite machine. The universe was simultaneously blindingly bright and completely opaque. You couldn't see through it. Then, At about 380,000 years after the Big Bang, the universe had expanded and cooled enough to reach a critical threshold of about 3,000 degrees Celsius. At this temperature, the frantic energy of the particles subsided enough for electrons to be captured by atomic nuclei, forming the first stable atoms of hydrogen and helium. This event is known as recombination. In a single cosmic moment, the free electrons that had created the opaque fog were locked away inside atoms. Suddenly, the cosmic fog lifted. The universe became transparent for the very first time. The light that was trapped everywhere was finally set free, released to travel unimpeded across the cosmos in all directions. And that light has been traveling ever since. The echo of creation, that primordial light, has now journeyed for 13.8 billion years to reach us. But it is not the bright, visible light it once was. Over its vast journey, this ancient light is all around us. It is the oldest fossil in the universe, the afterglow of the Big Bang itself. We call it the cosmic microwave background, or CMB. It was first detected by accident in 1965 by Arno Penzias and Robert Wilson, who were trying to eliminate a persistent, faint hiss coming from every direction in their radio antenna. That hiss was the sound of creation. Spacecraft like COBE, WMAP, and the Planck satellite have since mapped this ancient light with extraordinary precision. The resulting map, a famous oval image of mottled red, blue, and yellow, is arguably the most important image in all of science. It is a baby picture of the universe. When you look at the CMB map, you are looking at the ultimate wall of light, the very edge of the observable universe in time. We cannot see light from any earlier, because before this moment, the universe was opaque. This is our cosmic horizon. The different colors on this map represent unimaginably tiny fluctuations in temperature, just a few parts in 100,000. The red spots are slightly hotter and denser than average, while the blue spots are slightly cooler and less dense. These minuscule variations might seem insignificant, but they are everything. These were the seeds of all structure in the universe. Gravity worked on these tiny density differences over billions of years, pulling more and more matter into the slightly denser regions. These seeds grew into the first stars, the first galaxies, the great clusters and superclusters of galaxies we see today. They are the origin of our Milky Way, our Sun, and the Earth itself. You are looking at the blueprint for your own existence. Beyond the horizon, our journey has reached its end. We have traveled back 13.8 billion years to the oldest light, the surface of last scattering, our cosmic horizon. This defines the boundary of our observable universe, the sphere of space-time for which light has had time to reach us since the Big Bang. It might be tempting to think this is the edge of everything, but that is not the case. There is no scientific reason to believe the universe ends where our vision does. Our observable universe is simply the part of the total universe we can, in principle, see. The CMB is not a physical wall at the edge of space. It is a wall in time. Beyond that horizon, almost certainly, lies more universe. Much more. It could be hundreds of times larger than what we can see, or it could even be infinite. It likely contains more stars, more galaxies, more worlds, extending far beyond our sight. The light from those regions beyond our horizon has not yet had the 13.8 billion years needed to reach us. And because the expansion of the universe is accelerating, that light will likely never reach us. Those realms are, and will forever remain, beyond our direct observation. From the first questions asked around a campfire to this, a detailed photograph of the universe's infancy. We have pushed our senses to their absolute limit. We have reached our cosmic horizon. This journey has not only revealed the staggering scale and age of our cosmos, but it has also shown us our profound connection to it. We are forged from the elements created in the hearts of stars that were born from the clouds of gas seeded by the tiny fluctuations in this primordial light. To look far is to look back. And in looking to the farthest reaches of our past, we have found our own beginning. Our vision may have a limit, but our curiosity and our imagination do not. And as long as they persist, the great journey of discovery will continue. Messengers from beyond the wall of light, we stand at the cosmic horizon, gazing at a wall of light emitted 380,000 years after the Big Bang. This ancient glow, the cosmic microwave background, is the oldest light in the universe. It is the boundary of our vision, a shimmering curtain drawn across the universe's infancy. But human curiosity is relentless. A barrier is not just an end, it is a challenge. Is there any way to peer behind this curtain? Can we ever truly know what happened in those first, fiery moments when the universe itself was opaque? The answer, astonishingly, may be yes. Light, for all its glory, is not the only messenger in the cosmos. To see beyond the wall of light, we must listen for whispers from even earlier epochs' ghostly relics that were unfettered by the primordial fog. One such messenger is the neutrino. Neutrinos are phantom-like fundamental particles, so incredibly light and so weakly interacting with other matter that they can pass through a light year of solid lead without being stopped. Every second, hundreds of billions of them, produced by our sun, pass through your body completely unnoticed. This very elusiveness makes them perfect emissaries from the early universe. While photons were trapped in the hot plasma soup for 380,000 years, neutrinos were set free much, much earlier. They decoupled from the rest of matter just 1 second after the Big Bang. This means there should be an all-sky glow of primordial neutrinos, a cosmic neutrino background, CNB. That is a snapshot of the universe when it was a mere 1 second old. This relic would be the second oldest photograph of the cosmos we could ever hope to obtain. Detecting it, however, is one of the greatest challenges in modern physics. After traveling for 13.8 billion years, these neutrinos have lost so much energy that their detection is vastly beyond our current technological capabilities. Yet we know they are there. Their gravitational influence subtly affects the patterns in the cosmic microwave background and the distribution of galaxies. Scientists are developing ever more sensitive experiments deep underground and in the Antarctic ice, in the hope of one day capturing a single, definitive echo from the universe's first second. But there is an even more profound messenger, gravity itself. According to Einstein's theory of general relativity, cataclysmic cosmic events can create ripples in the very fabric of space-time gravitational waves. These are not waves of something traveling through space. They are waves of space-time itself. Since they barely interact with matter at all, nothing can stop them. They have been traveling across the universe since the instant of their creation, carrying a pristine record of their source. The most violent event in the universe's history was its own birth. The leading theory for the universe's first moments, called cosmic inflation, posits that in the first tiny fraction of a second, the universe underwent a period of hyper-accelerated expansion, growing from smaller than an atom to a colossal size in an instant. This unimaginable explosion would have created a storm of primordial gravitational waves. If we could detect these waves, they would provide a direct window into the first 10 to the minus 32 seconds of existence. This is the holy grail of observational cosmology, way to bypass the wall of light and directly witness the physics of the Big Bang. Observatories like LIGO and Virgo have already detected gravitational waves from colliding black holes and neutron stars, opening a new era of astronomy. The next generation of space-based detectors, like LISA, is being designed with the hope of one day catching the faint, primordial hum of space-time itself, the true echo of creation, the recipe for a universe. While we search for these new messengers, the cosmic microwave background remains our most detailed guide. The tiny temperature fluctuations within it are not random noise. They are the genetic code of the cosmos. But how did these microscopic variations, mere 1 part in 100,000 ripples, blossom into the magnificent galaxies and vast cosmic structures we see today? The answer lies with an invisible and mysterious architect, dark matter. The matter that we know and love: protons, neutrons, electrons, the stuff that makes up stars, planets, and people, is what scientists call baryonic matter. It accounts for only about 5% of the total energy and matter content of the universe. About 27% is made of a substance we cannot see, touch, or detect directly in any way, except through its gravitational pull. We call it dark matter. Its role in the story of creation is absolutely essential. In the early universe, the hot plasma of normal matter and radiation was locked in a cosmic dance. The pressure of the intense light pushed matter apart, while gravity tried to pull it together. This prevented normal matter from collapsing into structures. But dark matter felt the pull of gravity while being completely immune to the pressure of light. It did not see or interact with photons. Therefore, long before the universe became transparent, clumps of dark matter began to form in the regions that were initially slightly denser. They created what are known as gravitational wells, pockets of intensified gravity in the cosmic void. When the universe finally cooled and light was set free at the 380,000-year mark, normal baryonic matter was finally free to fall. And it fell right into these pre-existing gravitational wells that dark matter had been busy carving out for millennia. Without dark matter as a gravitational scaffold, normal matter alone would not have had enough time to clump together to form the galaxies we see, especially the early galaxies being discovered by the James Webb Space Telescope. Large-scale computer simulations that include the effects of dark matter are astonishingly successful. They show that over billions of years, gravity organizes this matter into a vast, interconnected network known as the cosmic web. Dark matter forms long, invisible filaments stretching across millions of light years, connecting at dense nodes. Galaxies form and evolve along these filaments like beads on a string of celestial silk. The empty spaces in between, known as voids, grow larger. When we map the positions of millions of galaxies in the sky, what we see is not a random scatter, but this exact web-like structure. We are seeing the visible matter tracing the invisible architecture of the universe, an architecture laid down by dark matter and seeded by the tiny fluctuations from the dawn of time. Inflation and the seeds of everything. This raises an even deeper question. Why was the early universe so incredibly uniform in the first place? And where did those perfect structure-seeding fluctuations come from? The CMB map shows that the temperature of the primordial universe was almost precisely the same in every direction we look. This is a profound puzzle. According to the standard Big Bang model, two opposite points on the CMB sky were never in causal contact. They were too far apart for light, or any information, to have traveled between them in the first 380,000 years. So how could they know to be at the same temperature? This is known as the horizon problem. The leading theory to solve this and other cosmological puzzles is cosmic inflation. It proposes that the universe, in its very first moments, went through an exponential, faster-than-light expansion. Before this expansion began, the entire region that would become our observable universe was an unimaginably small, dense point, small enough to have reached a uniform temperature. Inflation then took this tiny, smooth patch and stretched it to astronomical proportions in an instant, preserving that uniformity across our entire cosmic horizon. This solves the horizon problem, and it also solves another puzzle: why the geometry of our universe is flat. According to general relativity, space-time can have a curvature, but our measurements show the universe to be incredibly close to flat on large scales. Inflation explains this elegantly. Any initial curvature would have been stretched out and flattened, just as the surface of a tiny balloon becomes much flatter as you inflate it to a gigantic size. But inflation's most stunning prediction relates to the seeds of structure. The pre-inflationary universe was a quantum realm, and in quantum mechanics, even a perfect vacuum is not empty. It seethes with quantum fluctuations, tiny, ephemeral jitters in energy that pop in and out of existence. During the hyper-accelerated expansion of inflation, these microscopic quantum jitters would have been stretched to macroscopic astrophysical scales. These stretched-out quantum fluctuations became the tiny, real-world differences in density and temperature that were imprinted on the universe. These are the very fluctuations we see in the cosmic microwave background. In a mind-boggling leap of scale, the largest structures in the universe galaxy superclusters, stretching over hundreds of millions of light-years, originated from the smallest possible quantum jitters in the first fraction of a second of time. Our entire cosmic web is a quantum fluctuation made real, a universe fine-tuned for observation. Our journey to the cosmic horizon has revealed a grand, coherent narrative. A quantum event during inflation seeds the universe. Dark matter builds an invisible scaffold. Normal matter populates that scaffold, igniting into stars. Those stars forge heavier elements in their cores, elements which are then scattered across space. From this stardust, new stars, planets, and eventually, life can emerge. This leads us to the most humbling and perhaps the most profound realization of all. The universe does not just exist. It has evolved a part of itself, us, that can observe and comprehend it. We are not separate from this cosmic story. We are a product of it. And this leads to a final, startling observation known as the fine-tuning problem. When we examine the fundamental constants of nature, the speed of light, the strength of gravity, the mass of the electron, the value of the cosmological constant driving cosmic acceleration, we find that their values appear to be exquisitely tuned for the existence of life. If the force of gravity were slightly stronger, the universe would have collapsed back on itself long ago. If it were slightly weaker, stars and galaxies would never have formed. If the nuclear forces were different, by just a few percent, stars wouldn't be able to forge carbon and other elements essential for life. The universe appears to be balanced on a knife's edge. Why is this so? Why do we find ourselves in a universe with laws so perfectly suited for complexity in consciousness? Science offers no definitive answer, but several compelling possibilities. Perhaps it is pure coincidence, a brute fact of our existence. Or perhaps there is a deeper, undiscovered theory, a theory of everything, that necessitates these values, showing us they could not have been any different. A more exotic, yet scientifically plausible, idea is that of the multiverse. Our universe might be just one bubble among an infinite sea of other universes, each with its own randomly assigned physical laws and constants. In the vast majority of these universes, the conditions would be sterile and lifeless. But with an infinite number of universes, it is statistically inevitable that some, like ours, would happen to have the right combination of properties for life to emerge. By this logic, we naturally find ourselves in one of the universes where we could exist. This is the anthropic principle. We stand today, stardust looking back at its own cosmic genesis. We have traced our origins back to a wall of ancient light, peered behind it with the ghosts of neutrinos and the echoes of gravitational waves, and found our ultimate beginnings in the quantum flutter of the infant cosmos. The cosmic horizon is more than just a physical boundary in time. It is a mirror. In studying it, we see not just the birth of spacetime, stars, and galaxies. We see the impossibly long, complex, and finely tuned chain of events that was necessary for our own consciousness to awaken. The universe has produced a part of itself capable of looking back and asking, where did I come from? The ability to even ask that question may be the greatest wonder of all. The journey is far from over. The horizon may mark the edge of our sight, but it will never mark the edge of our curiosity. A universe among universes, the multiverse hypothesis, the idea that our universe is finely tuned for life, is both exhilarating and unsettling. It places us in a seemingly privileged position within the cosmos. The anthropic principle that we observe these specific conditions because we could not exist to observe any others provides a logical framework, but it doesn't truly explain the origin of this fine-tuning. For many physicists, a compelling, albeit mind-bending, possibility emerges from our most advanced theories. Our universe may not be the only one. We may inhabit a single island in a vast cosmic archipelago, a multiverse. This is not a concept born of science fiction, but a potential consequence of two of our leading theoretical frameworks. The first comes directly from the theory of cosmic inflation, which so perfectly explains the flatness and uniformity of our own universe. The model of eternal inflation suggests that while inflation stopped in our pocket of spacetime creating our Big Bang and the universe, we know it did not stop everywhere. Beyond the boundaries of our observable universe, the process of hyper-accelerated expansion may be eternal, continuing to stretch spacetime and constantly spawning new bubble universes, each potentially with different initial conditions. Imagine an infinitely vast pot of boiling water. Our universe is like a single bubble of steam that formed, expanded, and cooled. But the water all around it is still boiling, ceaselessly creating more and more bubbles. In this scenario, Big Bangs would not be unique events, but common occurrences throughout a much larger, eternally inflating metaverse. The second pathway to a multiverse comes from string theory. As an attempt to unify quantum mechanics and general relativity into a single theory of everything. String theory posits that the fundamental constituents of reality are not point-like particles, but tiny, vibrating strings of energy. A key prediction of the theory is that our universe must have more than the three spatial dimensions we experience. These extra dimensions are thought to be curled up into incredibly small, complex shapes known as Calabi-Yau manifolds. The critical insight is that there are an enormous number of ways these extra dimensions can be folded, perhaps 10 to the power of 500 or more. Each distinct configuration would result in a different vacuum energy and consequently, a universe with its own unique set of physical laws and fundamental constants. This vast array of possibilities is known as the string theory landscape. Our universe, with its particular laws and life-friendly constants, would simply be one possible valley in this unimaginably vast landscape of realities. If a multiverse exists, the fine-tuning of our universe ceases to be a profound mystery and becomes a statistical inevitability. With countless universes, each with a random shuffle of physical laws, it's not surprising that a few or even many would happen to have the right combination for stars, chemistry, and life to emerge. We find ourselves in one of the lucky ones simply because we could not have found ourselves anywhere else. Yet, this elegant solution comes with a tremendous scientific price. How could we ever prove or disprove the existence of other universes? They are, by definition, causally disconnected from our own. We cannot send a probe or receive a signal from them. This lack of testability has led many to argue that the multiverse is not a scientific theory, but a philosophical one. However, some speculative ideas for indirect evidence have been proposed. For instance, if another bubble universe had once collided with ours in the distant past, it might have left a subtle circular bruise or a cold spot in the cosmic microwave background. Scientists have searched for such anomalies, but so far, no definitive evidence has been found. For now, the multiverse remains a tantalizing, unproven, yet mathematically plausible extension of our cosmic journey. The question of the beginning. Before the Big Bang, our journey back in time took us to the cosmic microwave background. And with theoretical tools like inflation and messengers like primordial gravitational waves, we have tried to probe the very first fractions of a second. But this still leaves the ultimate question unanswered. What happened before the Big Bang? What, if anything, set the entire process in motion? The classical view derived from a direct interpretation of Einstein's equations. is that the universe began from a singularity. This is a point of infinite density, infinite temperature, and zero volume, where all the known laws of physics break down. Physicists are deeply skeptical of actual infinities in nature. They are typically a sign that a theory is being pushed beyond its limits, and that a new, more fundamental theory is required. To truly understand the origin of the universe, we need a theory of quantum gravity, a marriage of general relativity, which describes the very large, and quantum mechanics, which describes the very small. We do not have such a theory yet, but it has not stopped cosmologists from developing models that attempt to avoid the singularity. One such model envisions a bouncing universe. In this scenario, our Big Bang was not the beginning of time, but rather a point of transition. Perhaps the universe existed before, in a contracting phase. Over eons, it collapsed under its own gravity, becoming hotter and denser, until it reached a point of maximum density, not an infinite singularity, but a state where quantum gravitational effects became so powerful that they repelled all matter and energy, causing a big bounce. Our current expanding universe would be the aftermath of this bounce. This concept can even be cyclical. Our universe might one day stop expanding, begin to contract, bounce again, and start a new cycle. In this grand vision, the cosmos has no beginning and no end, only an eternal series of births and rebirths. Another possibility, emerging from quantum field theory, is the idea of the universe from nothing. It is crucial to understand what nothing means in a quantum context. It is not a void of absolute nothingness. It is the quantum vacuum state of minimum energy, but one that is still seething with potential. Virtual particles and energy fields flicker in and out of existence for fleeting moments. Some physicists, like Lawrence Krauss, have popularized the idea that the laws of quantum mechanics could allow for a larger, more permanent fluctuation to occur. A fluctuation that, under the right conditions, could tunnel its way into existence and, powered by the mechanism of inflation, blossom into a universe like ours. In this view, the universe has a net energy of zero. The positive energy of matter and radiation is perfectly balanced by the negative energy of gravity. Therefore, creating a universe from this quantum vacuum wouldn't violate the law of conservation of energy. This suggests that the origin of the universe may not have been a supernatural event, but a natural one, the ultimate free lunch. These models, the bounce, the universe from quantum nothingness, are highly speculative. We currently lack the ability to experimentally test them, but they represent a monumental shift in our thinking. The beginning may not have been a singular, absolute moment of creation, but rather a phase transition, a transformation from a previous state that is currently beyond the grasp of our understanding. The ultimate fate, a journey into twilight, having journeyed back to the very dawn of time. The final leg of our cosmic story takes us in the opposite direction into the deep, unfathomable future. The same forces that have shaped the universe's past are now determining its ultimate fate. And the key player in this final act is the most mysterious entity in our cosmic inventory: dark energy. Constituting roughly 68% of the universe, dark energy is the name we give to the unknown influence that is causing the expansion of the universe to accelerate. While gravity works to pull galaxies together, dark energy acts like an anti-gravitational force, pushing them apart with increasing speed. The discovery of this cosmic acceleration in the late 1990s was a complete shock, and it fundamentally altered our picture of the universe's future. If dark energy remains constant or continues to grow stronger, our cosmic horizon will shrink. Not our past horizon, which is fixed, but our future one. Galaxies beyond our local group, like Andromeda, which are gravitationally bound to us, will eventually merge with the Milky Way to form one giant Milkomeda galaxy. But every other galaxy, every single one of them not bound to us, is currently being pushed away by the accelerating expansion. One by one, their light will be so redshifted that they become invisible. In about 100 to 150 billion years, all galaxies beyond our local supercluster will have receded beyond our reach, their light no longer able to cross the expanding gulf of spacetime to get to us. The night sky for future astronomers will be a lonely one, containing only the stars of our own massive merged galaxy. The rest of the universe will have vanished, seemingly into an abyss, leaving our descendants cosmically isolated. But the story doesn't end there. It stretches into timescales so vast they defy human imagination. This begins the stelliferous era, the age of stars, which we currently live in. It will last for trillions of years. Stars will continue to be born, live their lives, and die. Eventually, however, perhaps 100 trillion years from now, the gas needed to form new stars will be exhausted. The last star, a faint red dwarf, will finally exhaust its fuel and sputter out. The era of starlight will come to an end. The universe will go dark. This ushers in the degenerate era. The only objects left will be the stellar corpses, white dwarfs, neutron stars, and black holes, all slowly cooling towards absolute zero. Over unimaginable periods, quadrillions upon quadrillions of years, these degenerate objects will occasionally interact. Galaxies will dissolve as their stellar remnants are ejected into the intergalactic void. Then, an even more fundamental process may begin. Some grand unified theories of particle physics predict that protons, a fundamental building block of matter, are not perfectly stable. They are expected to decay, with a half-life of perhaps 10 to the power of 36 years or longer. If this is true, then over these immense timescales, all baryonic matter will disintegrate. The stellar remnants, planets, and gas clouds will slowly evaporate into a bath of low-energy photons and other particles. The universe will become a thin, featureless soup. The final actors left on this cosmic stage will be black holes, but even they are not eternal. According to Stephen Hawking, black holes themselves evaporate over staggering timescales through a quantum process known as Hawking radiation. A stellar mass black hole will take about 10 to the power of 67 years to evaporate. The supermassive black holes at the centers of galaxies will take much longer, perhaps 10 to the power of 100 years. As the last, largest black hole radiates away its final particle of energy in a faint puff, the universe will enter its final state. This is the heat death, or the big freeze. The universe will be a cold, dark, and unimaginably vast void, filled only with a dilute sea of photons, neutrinos, and other stray fundamental particles, drifting aimlessly through a near-perfect vacuum. All structure, all complexity, all life, and all memory will be gone. Time itself will lose its meaning in a universe that has reached maximum entropy, a state of ultimate, unchanging equilibrium. This vision of a cold, empty end is a chilling one, but it is the fate that our current understanding of physics points toward. It is the logical conclusion of the cosmic journey that began in a flash of incomprehensible energy, a journey of breathtaking complexity that ultimately returns to profound simplicity. Our existence appears to be a fleeting moment of warmth and light between two eternities of cold and darkness, a brief, glorious opportunity to look up and wonder. The meaning in a fleeting moment, our place in the cosmos. We have journeyed to the dawn of time and peered into the abyss of the distant future. From the quantum flutter that seeded the cosmos, to the glorious fleeting era of stars and life, and finally to the predicted cold, silent emptiness of the heat death, our cosmic story unfolds on scales that challenge the very limits of human intuition. It is a story of magnificent creation and inevitable decay, a grand narrative in which our own existence appears as little more than a brief, incidental flicker. A more sobering solution is the Great Filter Hypothesis. This idea posits that there is some barrier, or a series of them, that is so difficult for life to overcome that almost none of it ever reaches a technological stage. This filter could be in our past or in our future. If it is in our past, we are extraordinarily lucky. Perhaps the initial leap from non-living chemistry to life, abiogenesis, is the filter, and it almost never happens. Or maybe the evolution of multicellular organisms or consciousness is the insurmountable hurdle we somehow passed. But if the great filter lies ahead of us, our future is precarious. Perhaps all technological civilizations inevitably destroy themselves through nuclear war, environmental collapse, or misuse of powerful new technologies like artificial intelligence. If this is the case, the silence we hear in the cosmos could be a dire warning. The empty universe would not be a sign of our specialness, but a graveyard of failed civilizations that came before us. Whatever the answer, the Fermi paradox frames our cosmic loneliness and reinforces the preciousness of what has emerged here on Earth. It urges us to cherish and protect this island of mind in a seemingly empty cosmic ocean. Our search for others is, at its heart, a search for context and for kinship, a desire to know if we are a solitary thought in a great silent mind, or just one voice in a vast cosmic choir. The horizon within, the future of knowing our journey to the cosmic. Horizon has revealed a universe far stranger and more magnificent than our ancestors could have ever conceived. We've learned that we are made of stardust, that we live on a pale blue dot in an expanding cosmic web, that our universe had a fiery beginning and may have a cold, dark end. We have constructed a powerful and coherent creation story based not on myth, but on evidence, observation, and the universal language of mathematics. And yet, for all we have learned, the true horizon may not be the one in the distant past, but the one that lies ahead, the boundary of our own ignorance. We still do not know what dark matter and dark energy, which make up 95% of the cosmos, truly are. We still lack a theory of quantum gravity to describe the moment of the Big Bang, the origin of life. Itself remains one of the greatest unsolved mysteries. We are surrounded by profound questions. But this is not a cause for despair. It is the engine of our future. The story of science is the story of continually pushing back these boundaries of ignorance. Each new discovery, each answered question, does not lead to a final, boring conclusion. Instead, it reveals a deeper, more subtle, and more beautiful layer of reality, opening up a whole new landscape of questions to explore. The joy is not in having all the answers, but in the relentless, thrilling pursuit of them. We began our journey by looking up at the night sky. Now we end it by looking back at ourselves, armed with a cosmic perspective. To understand the universe is to understand our place within it. We are not insignificant. We are improbable. We are not separate from the cosmos. We are its momentary self-awareness. We are stardust that has evolved the ability to contemplate the stars. The laws of physics that govern the far-flung galaxies are the same laws that govern the firing of neurons in our brain. The elements forged in the heart of a dying star are the same elements that allow us to hold a pen, to build a telescope, to write a poem. Our quest to understand the universe is, in the end, the most profound act of self-discovery. The cosmos is vast, and our lives are short, but in this brief window of time, we have been granted the remarkable privilege of looking out, looking back, and understanding a part of the grand story of which we are an inseparable piece. Our journey to the horizon has shown us that while our physical reach may be limited, the reach of the human mind is bounded by nothing at all.